contribution comes from the University of Cincinnati Department of Chemical Engineering. The speaker is Jian Huang. The authors are Jian Huang and Vadim Kulians. The topic is structure-directed synthesis of ECM-1, the novel interrupted alcohol framework.
Good morning, everyone. I'm very glad to have a chance to give a talk here. My title is The Structure-Directed Synthesis of ECM-1, a novel open aluminophosphate framework. First of all, I'd like to introduce something about macroporous materials. Macroporous materials are a family of inorganic solids that have pores with range from 5 to 20 angstroms. And here are some typical topologies of macroporous material. Here we show zeolites, aluminophosphates, and allophosphates. These materials possess unique Pau structures and active sites for separation and catalysis. Tetrahydroaluminophosphate frameworks is discovered in 1980s by Union Carbide, and this framework is connected by strictly alternating aluminum oxygen phosphorus linkage, and its framework is a four-connected tetrahydro framework. And by this strict alternation, this framework is neutral. And but since the aluminum oxygen phosphorus angles are very flexible, there are a lot of structures. There are altogether over 30 topologies known. Most of the aluminophosphate frameworks are synthesized by hydrothermal method, but until now there are very little practical application. This may be because that there are lack of framework active sites in this framework. Interrupted aluminophosphate frameworks depossess bronze-status axis groups in the frameworks, and thus they may have application in catalysis. TEL frameworks is constructed by aluminophosphates with the aluminum to phosphorus ratio not equal to 1. And the building units are not only aluminum and phosphorus tetrahydro, but also other building units. And this leads to rich structure and compositional diversity. Most of these frameworks were synthesized by solvothermal method. This is to use organic solvents instead of water as solvent in the synthesis. In this material, there are strong interactions between the template molecules and the frameworks, so they show poor thermal stability. Though they have these bronze-status axis groups in the frameworks, but until now there are no application in catalysis have been explored. Another aluminophosphorus oxygen framework is a organofunctional framework. This is a very novel material. The idea is to incorporate organic functional groups in the pore. You see here, this is inorganic frameworks, and we have organic groups that was incorporated into the framework. And thus, there is possibility to design macro-Pau shape and size, as well as controlling the channel wall properties such as hydrophobicity. So this material has potential applications in shape-selective catalysis and also chemical sensors and other uses. Here I give you an example. It's aluminum methylphosphonate. The linkage is, this is the phosphonate group, and it's linked by an oxygen to aluminum tetrahydro. I think this is a very promising aluminum phosphorus oxygen framework, but it's in very initial stage. There are still a lot of work to do on this framework. Aluminum phosphate frameworks, we can take it as a subset of aluminum phosphonate. I showed just the previous slide. We can take the methyl group and substitute by hydrogen, and then we form aluminum phosphate frameworks. There are some study before. There are mainly two previous synthesis methods. First is using aluminum nitrate and phosphorus acid and adjust the pH to 1.8. And another method is to modify existing aluminum phosphonate phases by melting phosphorus acid. But there are, comparing with the diverse frameworks of aluminophosphate, there are only one phase known until now for the aluminophosphate frameworks. And the most important is that there is no structure direction effect explored. So we investigated the structure direction effect and report here a new framework, ECM-1. This stands for University of Cincinnati material. This is the first material in our lab. Our synthesis approach is basically a hydrothermal approach. The source materials are aluminum hydroxide, phosphorus acid, and water. And we use organic molecules as structure directing agent. The list here is the organic molecules we tried. And the reaction temperature is from 100 to 150 degrees C. The reaction time is from hours to days. Here I will show the results for cyclohexamine as structure directing agent. We explored the phase diagram for aluminum phosphate and structure directing agent system. Here we selected points that corresponding to different reactant ratio, and we carry out synthesis by these reactant ratios. And we found that there are three different phases. First of all, we call it UCM-1. It has the structure shown here. This is XRD spectrum of this phase. And another two phases, which is UCM2 and UCM3. Both of them show different XRD spectrum with this UCM-1. UCM2 and UCM3 show a low 2 theta angle under 10 degrees. This may corresponding to large rings. But there is a problem that for these two phases, it's very hard to synthesize large crystals. So we cannot carry out the single crystal analysis by conventional method. So we send these two materials to Brookhaven and also argon for synchrotron analysis. But UCM-1 here, we solve this structure, and I'll show you the results. Here is so that I'll show the structure of phase UCM-1, but UCM-2 and 3 is still under study. Here is the crystals from the UCM-1 phase, and we were successful to synthesize very large crystals. They are regular, cubic shape, and with dimensions larger than 100 micron. And the empirical formula is found to be this by ICP and also CHN analysis. This is a structure solved by single crystal analysis. We can see that in this structure, we have corner and edge shared 4 membranes, and this may form a very large cage. And this framework, the units of this framework is connected by the oxygen 10 here and here. And also this forms an infinite chain, and these chains are linked by oxygen 11 here. It's not very clear, I'm sorry. But by single crystal analysis, we cannot establish the cyclohexamine we use. But when we carry out IR, we found that in the region of 2800 and 3000, we found binds that corresponds to the nitrogen hydroxide from cyclohexamine. And this confirms that the presence of cyclohexamine in the structure. This is the TGA analysis. We use a temperature profile. We carry out the TGA by increasing the temperature at 10 degrees per minute, and studied the thermal behavior of this material. And we found that altogether there are about 20% weight loss. But by calculation, the water in this material is about 15%. So this weight loss corresponds to loss of water as well as cyclohexyamine. And by calcium sample at 600 degrees C under iron, we found that the sample tends to gray, and this indicates that cyclohexyamine may be trapped in the structure. Also, XRD spectrum of calcium sample shows that the calcium sample is amorphous, so the structure may collapse with the removal of cyclohexyamine. Thus, the ECM-1 material showed limited thermostability. To study the structure-directing agent effect, we carry out synthesis with cyclohexyamine as well as without cyclohexyamine. For this synthesis, we use ammonium hydroxide to adjust the pH to the same value as the reactant mixture with cyclohexyamine. And this is the XRD spectrum of the samples from with and without cyclohexyamine. And we found that though the spectrum of the samples from without cyclohexyamine is very weak, but most peaks appeared at the same position with this with the sample from with cyclohexyamine. And this and we saw that the cyclohexyamine may lead to fewer nucleation sites, and thus they can form larger crystals with cyclohexyamine. And here is a summary of this talk. First of all, we started a self-assembly of aluminophosphate oxygen frameworks in the presence of cyclohexyamine as structure-directing agent. And this ECM-1 material possesses a large single crystal size, and the structure-directing agent molecules are located in the framework as Paul filler. But ECM-1 has limited thermostability. And for further study this system, we will use NMR characterization of template location and coordination. And we also will employ the effect of amine dissociation constant and unstructured reaction. And that's the talk. Thank you.
We have time for a few questions.
Any idea about pore sizes and pore structure? Tubular.
What? I'm sorry?
Pore structure, is it tubular?
Is tubular?
Is it?
You mean the pore structure I showed here?
Yeah.
The shape of the pores, is it like a cylinder, or is it going in 2-3 dimensions?
I think it's a three-dimensional framework that with these four membranes that form large ridges. I cannot tell you it's channel or cylinder. It's not regular shape. The channels.
The hexylamine interaction with your framework, is it a chemical interaction, or are you seeing a polar interaction? As such, can you exchange anything in and out for that? How mobile is that hexylamine?
Yeah, actually, that's the next we should study. We will use NMR to study the interaction, but